Good afternoon, everyone. I hope you're all having a lovely day. Yes, I'm Kit. I'm a technical consultant at Wolfram. So, today we are going to be talking about getting started with AI. So, without further ado, let's get right into it. So, first, I'm going to give a bit of an outline of what I'm going to talk about. So I'm going to go into some basics. I'm going to go into some machine learning in Wolfram Language, some quick examples of that, going to a bit more complicated things. I'm going to talk about some feature extraction, and then I'm going to show off some classification, some prediction, and then touch on some neural networks. But just before I actually get right into that, I do just want to AI is this term that like people throw out all the time these days, and it's quite a vague term in of itself. It's obviously artificial intelligence, but the way I like to think of it, it's a computer system that's kind of showing reasoning to perform a certain task. And so machine learning is a subsection of AI. It's something that we're going to talk about. This webinar is mostly focused on machine learning, but you should appreciate that AI is, a wider scope than just machine learning. All machine learning is AI, but not all AI is machine learning. There's other examples, such as symbolic AI. So, you've got your Wolfram Alpha. But anyway, let's focus on what we're supposed to talk about, which is, machine learning. And let's get started with that. So, what is machine learning? So, at a fundamental level, machine learning is where you have a computer or a machine where you have a model that learns from a set of data. And when we're talking about a model, we mean a program with parameters. And when we're talking about learning, we are talking about how you are tuning those parameters to fit the data. So in this instance here, we've got some data points on some coordinates, and then we want to generate a model that can predict for us a given y value for a given x value. So, you know, in a sense, we are generating a function, we're generating a model or a curve which will fit this data so we can, predict it for unseen values. And the learning in this case, we are tuning this function, this model, and that can be, via a range of mathematical transformations. So we can apply some exponential to it. We can multiply it. There's a vast amount of things we can do to alter this curve so that it matches the data. Now, if we think about a more complicated example, something like image recognition, which is a huge part of AI machine learning, we kind of want it to take in an input of an image of a cat and then correctly identify it as a cat. And the same case with a dog, we want to be able to identify that image as a dog. And so this is a much more complicated task and requires a lot more complicated machinery. So something like this, we're going to use something like a neural network to perform this task, which is a hefty set of kind of regression in organized in a network, but we'll talk about that a bit further on. So you can kind of subdivide machine learning itself into some categories, which I'm going to talk about now, and you can do that. There are more, but these are probably the most relevant or the most, uh, yeah, I guess relevant. So you can think about supervised learning. Now, this is when you have you are training your model with where you have input data which is mapped to a truth value. So see here like for example, we've got an image of a cat. Now we've mapped that to a truth value of a cat. And same here, dog, we've mapped that to a dog. So, through this we are able to kind of like this is particularly helpful for something like image recognition. We're giving it true values, and so the true values kind of represent the supervisation that we are performing for the model. We're kind of guiding it to the correct answer. Now, this is the most common type of learning, and it's really good for when you've got labeled data. So something like image recognition is going to be pretty good. Expanding out, we've also got some, we've got some unsupervised learning where, you don't have labels to that data. You've only got the inputs. Now, this is good for when you want to identify patterns in data or clusters. So something this might be useful, if product recommendation. If the machine learning model is given some data about me, so I'm 25, I'm male, I'm kind of sporty, it might want to recommend me something like some nice running shoes or whatever, given those that data. Now, reinforcement learning kind of like ties both of these methods together a bit, and kind of it's a model that kind of gets feedback from environment. It kind of it learns from its experience and then is able to change its parameters given a particular how it's doing. So for learning to play a game, it's particularly powerful at that. So some of the typical tasks you might be doing when it comes to machine learning. So you might want to be doing some image classification. So computer vision is a massive field, and image detection is a big part of that. You might want to, as we've seen a few times now, identify cat as a cat, but also we might want to do some predictions. So given some input data, we might want to map that to a likely output data. So in this case, we've got, given the knowledge that we have a 6-year-old female, can we guess how tall she is? And this is giving a potentially pretty reasonable assumption. But I guess the key difference here between classification and prediction is in classification, you're kind of classifying to discrete values. So, it is either a cat or a dog. It's not anything in between. Whereas here we've got a continuous variable. It's either 1.5, 6, 7, 8, 9, 10, a various amount. So that's what we mean by prediction. But there's a lot of other things you can do. So if you want to do some text translation, so here we can, mapping some English to French via learning, to an extent French. But you might want to predict a time series. You might want to pick out some anomalies in your data, or you might want to cluster your data, or solve a maze. So things that kind of require some amount of reasoning based on data. It's required that it has learned something to perform these tasks. So let's go a bit further on. So firstly, I'm going to introduce a few things about the Wolfram language. Some of you may not be super versed in this, which is completely fine. I appreciate that. So I'll give a quick overview. So you quite often work in Wolfram language in a notebook. So right now I'm in a notebook right now. There's a presentation notebook, but it's it's similar to a Jupyter notebook if you've used that in Python, but pretty intuitive. You evaluate things and perform computations. You can do symbolic and numeric computation, wider range of things. You can do some natural understanding. So you can use Wolfram Alpha. You can quite often ask it a question in real English and it will break that down and appreciate it. And so that's actually one of the symbolic AI mechanisms I spoke about. It's not actually powered by machine learning, a slightly interesting thing. But within the Wolfram language, you also have access to a bunch of state-of-the-art algorithms, some built-in data, and you'll get this notebook, and you can play around, look around at this at your own time. We accept a variety of different data sets, and we have a very comprehensive documentation where it's just a good way to learn a bit more about a particular function or wider parts of the language in general. So recommend checking that out. Also, deployment's very easy if you want to deploy something to the Wolfram Cloud. So in terms of the actual syntax itself, so everything in Wolfram language is an expression, and we use functions to alter those expressions or do things with those expressions. But fundamentally, basically, at every time you have a function, you have a head of a function, you have some square brackets, and within those square brackets, you can provide arguments separated by commas. And then you can also set particular options to a function and ascribe those to particular values. Now you can nest these in particular ways, and these are evaluated from the inside out. So this particular expression, you have the head 3, apply that to argument 1. The output of that is then applied to head 2 with argument 1, etc., etc. So you can see that with, like, if I want to do +1 +1, this here is the head, this is argument 1, this is argument 2. There's no options for plus. It's a pretty fundamental mathematical function, so we're not going to alter with that. But yeah, so like just for your benefit, to those who haven't seen it before, it's a good way to know this. And so the head often describes what you're doing. So, big thing in machine learning, we have this classify function, and this kind of is the task that it's performing. Got square brackets. And yeah, so in terms of the data syntax, you can have lists, pretty standard computer science concept. So these are grouped into curly brackets, and you can contain your data within those. Now, there's no limit to how deep these lists can go. You can have lists of lists or list of lists of lists. There is no limit to how far you want to do that. So you can represent some pretty complex data. Now, another particularly important data structure is the association. So if any of you have used Python, these are very similar to dictionaries. It's just like this key value mapping. So here we've got a key of name. We map that to a value of Jim. So it's just a important way of having this key value mapping for quick lookup or representation of various datas. In the same way that we can have lists of lists, we can have associations of associations. Now, one nice particular function is dataset. So here, this is a postfix form. Here, it's just another way of applying this function dataset to this data. And dataset is just a nice way of representing some, in this case, non-rectangular association data. It's just a bit easier on the eyes, which is always good. So let's actually get into some machine learning in the Wolfram language. In the Wolfram language, you have access to many different functions, and these are often very task oriented. So the names of the functions are related to the task. So here we've got classify. This is related to the classification, or prediction is related to the prediction. So it's task oriented in the sense that you're not focusing on the methods just yet. You're not thinking like you're not applying like k nearest neighbor to a piece of data. You can kind of extrapolate away from that and just use classify or predict. And there's a bunch of these machine learning functions, and within the wider Wolfram ecosphere, there's thousands and thousands of functions, and function repositories on top of that. So you can do a lot of different stuff just out the bat. So these are automated and easy to use in the sense that it can quite often do everything for you. And we'll look at some examples at that in a bit. So you also have access to this neural network framework where, it's a very flexible framework. You can swap in and out particular layers as you want to. It's a good way of actually understanding neural networks itself, but also, applying neural networks itself. It's, Wolfram is a fantastic platform for education, but also doing some real research. And you also have access to high performance. We can, tailor this to be trained on GPUs, which is, very powerful thing these days, especially when it comes to complexity. So let's get at some quick examples. So I mentioned this classify function. So here, classify has, what are we doing? We're kind of classifying particular things into discrete categories. So you have access already right at the bat to a range of different, I think it's about 8 or 9 different classifiers built into classify. So here we've got the language classifier. So what we're doing is we're classifying that into a particular language category. So when we do classify language of quelle est cette langue in French, then we can output that as French. So the classifier has correctly used the um, classifier to predict or classify this into French. Doing that a bit further, we can look at this English statement, and we can actually generate the top probabilities. So an important thing you have to kind of take into account when it comes to machine learning is it's not necessarily correct, as when you do a computation in like the Wolfram language. Like if I do 2 to the power of 56, I can be confident this output is correct. However, with machine learning, you can't always be correct. This is how confident it is that this statement is in English. So, in this case, we can, I think, look at some more potential things. So it's looking at this and it's thinking, oh, it's pretty likely to be English, but it might be something like Tagalog, which I've never heard of, Afrikaans, or German. So that's a very important thing to bear in mind when using machine learning, like in general. So let's look at some image identification. So let's assign an image of a wolf to this wolf symbol and some limes to this lime symbol. So you have access. So there is this high level function image identify. And so what I mean by high level is that it's, very far removed from the actual implementation itself. All you have to do is apply this function to these data forms and you can get an output. So here, this is the map operator. So we are taking image identify and applying it to this image and this image. And it's identifying this as a grey wolf and identifying this as a key lime, which I'm assuming is just a lime. Also, you have access to, there is a neural network repository. So we at Wolfram have curated a bunch of different neural networks for you to use, play with, or perform some computations of your own. So we can go ahead, get this neural network, and then again, same thing, we are applying that to this wolf and this lime. In this case, it's identified this as a lemon. Maybe it's just a unripe lemon, who knows? But there's always going to be some amount of entropy when it comes to using machine learning. So also we can do some image restyling. So let's take a few images. You've got Mona Lisa by Da Vinci, this image by Kandinsky, and then this river by Vermeer. And assigning those, what we can do with image restyle is, we can use this machine learning function to take this image of Da Vinci and then restyle it in the style of Kandinsky. And then we get this wacky Mona Lisa rendition. So it's just a nice way of demonstrating what we can do with our machine learning techniques. So we can also we can use text structure, so we can operate on text. So big use of machine learning. So here, what we're doing, we're kind of doing some natural language processing itself. We are decomposing this statement into the core expressions. So the noun, verb, adjective, punctuation, and this is just a pretty cool thing you can do. Very important when it comes to machine learning if you're operating on text. So applying that, let's look at some examples of actually doing that. So let's get some data about the moon from Wikipedia with this function Wikipedia data. And then what we're going to do here, we're going to use this text cases. So we are going to identify in, there's the documentation behind text cases. We can take this moon data, and then what we're going to look for is we're going to look for particular quantities in this Wikipedia data. Now we're also going to we're going to interpret these in the Wolfram language. So what we're going to do is we're not just going to like grab things that look like quantities. We're going to interpret those into the actual objects in Wolfram language. So Wolfram language, you have access to these, entities of things that represent real world objects. So I can represent, 3 kilometers as 3 actual kilometers. So ideally, when this finishes, I can show that off. Yeah, we've got all these quantities that we got from Wikipedia data about the moon. And so it's useful to have them in this particular interpreted format, because now, say I want to have a look at the total, so the combined kilometers and miles, I don't have to worry about um, you know converting between units. It's all done that for me. It's abstracted that away from you. It just makes things a lot easier to, if you're working with quantities, to work in this with these Wolfram language entities, unit entities. So we can also go ahead and apply text cases. Let's pick out some of the nouns in the moon data. Let's then apply this counting function, which identifies the most. Well, it just counts every element of a noun, and then so yeah, now we're getting the 10 largest outputs of our counted nouns in moon data. See, we're getting 64 surfaces, 38 sides, etc., etc. So anomaly detection is another important field. So we can use this function to find anomalies and just give it some colors to work on to identify, which in this particular data set, what doesn't quite, what's not, what doesn't belong here. And pretty intuitively, you can see that all of these data points kind of follow a particular trend of color, whereas this red and this green, it doesn't necessarily belong here. So going ahead, we can do that a bit more complicated. So let's use some of our resource data, which we have access to in the Wolfram language. So this is the MNIST data set, which is a bunch of it's a bunch of like handwritten images, and then it's mapped to a particular yeah, so it's a bunch of handwritten images. And why is that not working? But yeah, it's mapped to some. Actually, I think if I do this, it should work. Maybe not. Oh well, but yeah, it's just a bunch of images, yeah, mapped to a output. So we're doing some supervised machine learning here. We are generating a anomaly detection function given this training data here. So we have generated this anomaly detection function. So now we are going to go ahead and apply find anomalies using this particular detector function, which has been trained on this resource data, where it's mapping handwritten images to numerical integers. Now let's go ahead and apply that to this data set to see if it can pick out the things that don't necessarily belong here. And here we've got this picture of a monkey, not necessarily an handwritten image, handwritten digit. And this one is just too noisy in comparison to the other data sets. It's not it's too static. It doesn't necessarily belong because of all the pixelation. So let's go a bit further on. So let's talk about feature extraction. So this is this is an interesting concept. This somewhat complicated, to be honest, but feature extraction, in a nutshell, is kind of when you're given some data, you're kind of looking to identify the core essence of the data. You're trying to capture the most significant the significant gist of that into a very condensed format. So in within Wolfram language, the machine learning frameworks, they are designed in such a way that they require numerical vectors as inputs. They can't necessarily operate on any kinds of data. So If we think about in our previous examples that we've literally just run on, we've worked on a range of different data sets. So we worked on some string text, some images, a range of different things. Now, for our machine learning frameworks to actually identify patterns behind that, it needs to identify the core essence, the kind of the features that underlie those pieces of data. Um, and this is actually quite a complicated thing, where you're trying to boil down certain data into numbers. It's hard. It's often hard to capture you know uh, information within numbers. But let's look at some examples of that. So we can use this feature extract function to kind of have a good guess at, given some input data where we've got a phrase, a color, and a date. Let's map that to here in this case, a three-dimensional vector which tries to capture that information. Now, in machine learning, you will or often, or you should hopefully have it works best with a lot of data. In this case, we haven't given it much data at all, and it's hard to argue that these features that it's kind of extracted into vectors are entirely representative of our input data. Like it's pretty easy to argue that some of the richness and essence of this phrase, "the cat is grey," is being entirely captured by this vector. So, you really want to be working on wider data sets to kind of capture the essence and the features so that you can identify patterns and, do your predictions, your classifications. We can also do this with, a range of different data sets. This is just operating on association rather than a list. But, feature extract kind of works with pretty much anything in the Wolfram language. So here we're actually operating on some graphs. So let's go ahead and look at those. So it's kind of boiled down these graph objects into these vectors here. So I guess what I should try and convince you is that these are features. They are representing some information about the input data. Now, an example of that might be, so in this case, we've got some graphs. This number here might be representing the density of the graph, or the number of nodes, edges, whatever. It might be a key feature about this graph. So in a similar way, what we're trying to do is we're trying to be able to identify the core features so that we can generalize that to unseen data. So if we think about how a human, so how do I recognize a cat as a cat? I'm looking at an unseen cat. I haven't seen it before, but I might identify the core features of that cat. So I might see the things that I believe are the features of the cat. So the pointy ears, the nose, the whiskers, these are all features that I know as a cat, and I can be like, "Oh, yeah, that's a cat." In the same way, that's what the machine learning algorithms are doing. They're identifying the core features of that data, and then being able to predict and classify that to unseen data, so that it can also do its you know, extrapolation of an unseen cat as a cat in a similar way. But it's important to realize that, when it comes to machine learning, like these values are actually, or these features even, are actually incredibly arbitrary and abstract. And often, I gave the example of density. This number is unlikely to be density. It's more likely that the machine learning algorithms are identifying things that we can't even notice, or we don't even have a word for. It might be something best described as the zigzaggedness, or a particular correlation of pixels in a certain way. It's very hard to identify what the machine learning algorithms are doing, and that's something a little counterintuitive, but you have to get your head around when it comes to machine learning. Let's let's kind of look at that in a bit more detail. So I'm going to start running these things here and then talk a bit more about them. So if we go ahead, go online and look at some images from characters from the Guardians of the Galaxy film, this here is just getting a bunch of images online. Hopefully it doesn't find anything dodgy, but hopefully that's all fine. And let's create a data set where we've got some character images um, from online of these Guardians of the Galaxy characters. And let's go ahead and let's improve our data set. So what have we got here? We've just got the character images itself. So we've got a bunch of groups, Star-Lords, etc., etc. Now let's go ahead and take a random sample and flatten that so we don't have any like order to this data set, and it's just completely random. And we can identify the core things without having some bias of if we have the order, it can intrinsically bias the data set. So what we can go ahead and do is we can create this feature extraction function using feature extraction to generate this extractor function, which is trained on this data set we've made to collapse down all of the information there into a particular vector, into a particular series of vectors. So then we can go ahead and apply this extractor function to an unseen image, and then this maps it to the vector space which it has been trained on. So this is what it has, it thinks it, or it's, it is capturing this image in terms of the vectors which it has learned from this. So yeah, we're turning it into numbers, so then we can go ahead and do some machine learning on that. Any unseen data. That's kind of how it's working under the hood. So we can also go ahead and create a nearest function. So we're using the same data set, and we're using this function here, future nearest, to generate a nearest function. So we're training a function so that it's when it's given unseen data, it will then identify the image in the data set which is nearest to the unseen data. And here you can see this image of Rocket Raccoon is in fact nearest this is nearest to this, which was in the training data set. So it's kind of taking this, it's boiling it down into its features, into its numbers, and then with those numbers, it is literally just mapping, or it's identifying that which vectors are numerically closest to our predefined vectors which we have in our data set. And that's literally what it's doing. And we can go ahead and do it here. So interestingly, in this case, it's done it incorrectly. This is an image of Groot, and this is not Groot. I think that's Star-Lord. But I mean, that's kind of the issue with machine learning, is it's more of a, this is what it's confident it is, not it's not necessarily correct. But what it may have done in this case is it may have looked at some of the features of this image. So it might have taken out the orientation of the person. So it's kind of, they're both looking to the right here. The color scheme, that might be what it's like identifying as the core features. And that might be closest to it in terms of vector space. So yeah, that's just something you have to be aware of. It's more about confidence rather than being categorically correct. So let's go ahead, let's look at this in a slightly different way. So let's take in our character images and then let's plot this in feature space. So in terms of X and Y. So here we might be doing that to kind of like look. So we've collapsed these vectors down into two coordinates, X and Y. And then we can kind of like use this feature space plot to kind of identify how well this this feature extraction is going. So if you can see some clustering going on, then you can get a good sense that, it's going pretty well. It's identified the core features of those images and then mapped that correctly to the um, particular images. And so yeah, we can see a cluster of groups. So what we're doing here, so feature extraction is very related to dimension reduction. It's a very related field. So when we're doing feature space plot, we can actually think about that a little bit more manually, and you can think about it in terms of dimension reduction. So earlier on, I think we had, how many features was it? So yeah, we had all these features here. I think that's about, you can have a look. 79 different features, different vectors. And then what we're doing here with dimension reduce is we're reducing that down into vector of 2 dimensions here. So we're boiling that down into, yeah, we're trying to capture more information in just 2 vectors instead of 79. Now that's like kind of an important process, not in just in terms of, I mean, you can think about it in a few ways, but like one way, when you're running the actual machine learning calculations themselves, when you're doing calculations with of vectors of dimension 2, it's a lot easier than with dimension of like 10th dimensions, 12th dimensions, and this is, better in terms of computation cost. It's just going to be a lot easier. So it's good in that sense, but also in terms of, um, we're actually just focusing on the core essence of it in these 2 vectors. So you may well be improving the performance of the model when you're not focusing on insignificant, useless features which don't necessarily correlate to features that you can make accurate classifications or predictions with. So having reduced these dimensions into these 2 spaces, we can then apply a list plot to kind of do that again more manually and look at some of that clustering in feature space. So let's look at some classification. So this is, a very important thing you will be doing in machine learning, and something you do in wider data science itself. It's a huge part of this. So let's kind of, I'm going to walk you through a bit of a method of how we go about doing that. So your typical steps of doing this is you're going to first of all prepare the data. Now this is actually a hugely important part because, in the real world, real data is never as organized as it is in, your online data sets. It's missing things, it's got anomalies, and so you have to prepare that data so that you can get meaningful outputs. When it comes to anything in data science, especially machine learning, if you have bad data, you're going to have bad performance. So having prepared that, we're then going to create a classifier. Then you're going to want to train the classifier on some training data and some testing data. So you will quite often want to separate your data out into training and testing data. And then you're going to go ahead and measure the accuracy of your classifier against the testing data. So I'm going to walk you through that a bit. So let's get some character data from those images again. Let's get a random sample, and let's split out our dataset into some training data and then some testing data. And then let's go ahead, let's do the second step. Let's generate a classifier of that. So again, here I'm trying to showing off how automated and easy it is to do some machine learning in Wolfram Language. All I had to do was run one function with one data set, and it's chosen everything for me. In this case, it's done a logistic regression method of machine learning to generate our classifier function. So let's go ahead and run this. So it's identified incorrectly. I think that's a rocket raccoon. It said Groot, so unfortunately, it's not done too well in that case. But so now let's run the character classifier. Let's have a look at the probabilities. It's thinking, so it's having a look at this image and it's trying to think, which one is it? So in this case, it's saying pretty strongly, it's thinking that this is Star-Lord, which is correct. And so when we're talking here, we're just extracting out the probabilities. We're trying to see what the neural network is thinking. Actually, it's not a neural network. Um, it's using logistic regression in this case. And then here we're just having a look at it applied against a bunch of testing data. So Groot, Groot, Gamora, 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 Groot, Groot. Yes, so it's done pretty well this time. That's good. Glad we got some decent performance in the end. So we can also, in Wolfram language, we can use, we can classify our classifier using classifier measurements. So we're giving it our classifier function itself, and then we're giving it some testing data. And this is kind of, giving a holistic overview of how this function is performing with regards to the testing data. So, you're getting an accuracy, we're getting a baseline accuracy. I mean, there's always going to be some accuracy that you want to get better at. I think there were 5 categories. So there's going to be some amount of, if you just guess Gamora for every single classifier, you have about a 1 in 5 chance of getting that right. I'm not sure why that's 30. It might be doing something a bit more complicated than that, but it's similar to 20%, which is 1 in 5. And then we can go ahead and look at that in a bit more detail. So we can extract out the accuracy, generate our confusion matrix plot. So this is, looking at a matrix of where it's done well. In an ideal world, you've got like this diagonal where it's done correctly. So we've got a predicted class and then the actual class. So here it's predicted Gamora correctly, Groot correctly. It's got that one wrong 6 times, Rocket Raccoon correctly, and then Star-Lord doesn't seem to be doing too well. But this is important. This is helpful to kind of infer you when it comes to retraining your model. This is helpful to know. So in this case, it's done pretty poorly on Star-Lord. So now from that, we can kind of infer that we need some more examples of Star-Lord to our data set. So we can go away, give it some new data, like retrain it on some new data with Star-Lord, and then we will eventually, create a better model. And so, what are the worst classified examples? Well, Star-Lord being Star-Lord. Yeah, so we want to get some more Star-Lords. That's not even slightly Star-Lordy. And then, yeah, in the opposite case, we can look at some best classified examples. Um, so let's have a think about some classification methods. So yeah, so let's go ahead and do another example. So let's get some colored points. Let's get some data sets where we've got these two reals, and they're mapped to a color. So this could represent a bunch of different things. So these could be coordinates wrapping to I don't know, a flag color or something like that. So let's take our data. Let's then create a classifier for that. So here I've told it to automatically choose the machine learning classification method for me. You don't actually have to do that. It will do it all for you. That's the nice automation at hand. But here it's chosen, the naive Bayes method. And so what you have to appreciate is different machine learning classification methods will net you different results. So if I'm using nearest neighbor, I'm going to get different performance to logistic regression. I think nearest neighbor is literally just taking into account which data point is nearest to it and then it's classifying that as just the nearest thing. Logistic regression, a bit more complicated. I think it's actually mapping a curve to it. And then there are a bunch more different ways of doing that. And you've also got these, neural networks, which can, do some pretty complicated classification using these multi-layered regression techniques, which is all pretty cool. So when it comes to actually choosing the machine learning method, it's pretty unintuitive in the sense because you can't really work out how or why it's come to a particular classification, but you should kind of focus more on like, is it working? Is it actually working for my data set? Like, we can generate, you know, these, we can quantify how well it's performing. And so we should focus more on the quantifications of performance rather than, oh, should I use this method in regards over another method? So with that in mind, what you kind of want to do is you want to test each method on a subset of the data and then actually just go ahead and choose the method that's giving the best predictions rather than focusing on which is the best method. And then go ahead and apply that to the entire data set. So I'm going to quickly walk you through that again. So let's get some training data of, so example data, it's just things you have access to in Wolfram Language of the Fisher iris, which is, I think it's just a quantification. Oh, it's just a mapping of some dimensions of particular irises to a particular species. So here we've separated it into training data and testing data. Now let's grab a random training sample. And then let's go ahead and create two classifiers, one using a Markov method and one using a random forest method. Now let's look at some measurements of that. So using Markov, we've got about 76% accuracy. Random forest, we've also got 76% accuracy. So they're both doing pretty well. So either would be valid methods to use. The performance is slightly different when you look at the confusion matrix. So if you go ahead and use the Markov method, then you might want to go ahead and add some more examples of versicolor because it's got that slightly incorrect occasionally. Again, we can create another classifier using a random forest, and then this is, again, so we're taking the random forest and then we're applying that to the whole data set and then seeing how well it does. So let's also think about prediction. So once this model has been trained on some data, we can then use it to predict some new values. So, as I mentioned in data science in real life, a lot of the times you don't have good data. You will quite often have missing data points. So if you want to fill in the gaps, you can actually use some prediction to kind of impute some new data points and improve your model. So just quickly, let's look at some. I think this is some house price data in Boston. So again, let's split those up. Let's create a predictor using predict, slightly different to classifiers we've looked at. It's using this particular method. We can get a little bit of examples of this. So now we're going to feed it in some input fields, and then we're going to try and get it to predict some missing values. So here we're going to try and get it to predict the MEDV, which is median value of owner-occupied homes in the thousands. So let's have a look at see what it does. So given these input fields, it's guessing that the median price is going to be this. We can go ahead and in the same way as classify, we can look at some predictive measurements and see how well it's doing. Going a little bit further, we can look at some neural networks. Now, these are a little bit more complicated, but these are where machine learning is going to be doing the most interesting and kind of exotic and spicy things even. So in the Wolfram language, you have a bunch of different examples of things you can apply to your neural network or build your neural network even. So these are particular layers of your neural network, which you can even build from scratch if you want. I'm not going to go into that today, but you can pick and choose your different layers to your neural network as you desire. So let's go ahead and look at that. So we can also grab our neural network from our repository. So let's grab the Linnet neural network. We can have a look at it itself. So it's composed of all these different layers. and we can represent that as just a symbol in Mathematica. And then we can go ahead and let's make some testing data, or again, on some MNIST handwritten training data, handwritten digit data. And then we can see how it performs when we apply it to some data, see how this neural network is identifying this input, and we're seeing what it's outputting. So it's looking at this, it's running it through this complicated neural network, and then eventually categorizing it in this case correctly as one. And in all these cases, it looks like it's done pretty well. So we can go ahead and, these neural networks are very interactive. We can do stuff to them. We can kind of alter them in any way we kind of want. So let's go ahead and look at an example of that. So first of all, let's blur these images so that they are looking a little bit more blurred. So yeah, a little bit more blurred in this case, and then let's apply that. Let's see how this neural network performs on this new data, which has been blurred. So it's probably going to make it a little bit harder. And as you can see, still does pretty well. It's seeing 2, 2, 3, 3. Oh, this time it's done incorrectly. 8, 9. So with this new data, it's not doing so well. So how about we go ahead and retrain that neural network? Let's give it some of our new data with our blurred data, which we've just made. And here you can get an insight into the training process. So we're looking to minimize the loss function, so how far it is from the training data, or how far the prediction values are from the training data, is kind of what we mean by loss function. And hopefully it doesn't take too much longer. And then, yeah, we've generated our new neural network, or retrained neural network. It hasn't actually changed necessarily. And let's apply that to some of that blurred data. And as you can see, it's doing a little bit better. We've successfully retrained our neural network on some new data, so it's factoring in some new features perhaps, and able to extrapolate that to some more difficult a more difficult data set, in terms of it's blurred, it's slightly different. But having said that, it also works when we're using the older data set. This is the original data. So when we run this retraining layer, we're not just completely removing all the parameters and all the predefined knowledge. We are kind of still maintaining a degree of that, so that we can still use it with our older data. So let's go a little bit further. So yeah, we can kind of modify and inspect these networks themselves. They are symbolic objects. We can do things to these objects. So we ascribed Linnet symbol to that neural network. So we can actually peel this back and kind of look into it itself. So when we run normal on the Linnet, we can look at the individual layers itself, that compose the neural network. And we can get a bunch of information about that. Now, if we want to look at that individual layer itself, we can do that. We can run another normal, and we get an association which is kind of returning all this interesting information about the layer itself. Yep. Okay. So let's create another image identifier. So let's go ahead and grab this image identify neural network from the neural network repository, ascribe it to this symbol. So there's another example of an image identification neural net, or just another example of some image identification. So here we have correctly identified this tiger as a tiger. Now we can go ahead and kind of peel that back a little bit more. So let's actually take the first 10 layers of the network and then apply it to that Tiger itself, and so we're kind of getting a little bit of insight into what the neural network is looking at, or kind of what it's seeing. So these are the vectors it's looking at, and if we can actually generate images of what the neural network is looking at at this 10th layer. So you might be able to see some degree of features about Tiger that looks somewhat tigerish, um, which is kind of interesting way of like peeling back what the network is seeing at a given layer. And so this is just going to be looking at some of the layers. So we're just looking at some of the dimensions of the layers of a given neural network, which is all pretty interesting. So when it comes, so something I want to touch on is generalization and overfitting. So when you have a model, you kind of want to avoid a model that remembers what it's seen um, from in terms of the data itself. Like you don't want it to remember too much about the data. You want it to kind of be able to generalize that data and then predict new things on unseen data, or classify things on unseen data. Now, a network that, or something that overfits is going to be pretty poor, or there's a kind of like a range of performance when it comes to this. So in the case of underfitting, we kind of have our data points, and then we have our model predictions, which are doing okay in some cases, but it's underfitting in the sense that it's not been able to capture the essence of the true function of what is in reality going on. And so this is going to be a poor represent. This is a representation of a poor model because it's unable to do anything particularly well. So here in the middle one, we've got some good fitting. So here it's been able to capture the correct essence of the data points and then been able to map that to a particular function. So in this case, we've got some overfitting. So this is what I kind of meant by it's learned the data, but not the underlying, the correct gist of what's going on. In this case, it's been given too much freedom to explore what the data, the patterns of the data, but not necessarily the patterns of reality. So this model function here is, it's going through pretty much every single data point correctly, but when you compare it to how it's doing against real data, against reality, against unseen things, it's going to do pretty poorly. So given an x value of this, it's going to be predicting it y as here, which is vastly overfitting and not doing particularly well. So it's kind of like Linnet against the blurred images. So let's look at that a bit further. So let's generate some data. So here I'm just making a table of an exponential function, and in reality we have a lot of noise, we have a lot of randomness to data. I'm going to throw in some randomness here. So it's not just an exponential function; it's an exponential function plus a certain degree of randomness. Now, if we plot this, this is what our data points is looking at, not what reality is looking like. Well, I'll get onto that in a second. So this is our data. Now let's go ahead and I'm going to create a neural network. So here I'm going to give it 150 layers initially. I'm going to use a tanh activation function, which is kind of like, given a certain value threshold, it's going to give me a yes or no value to kind of boil it down. So let's make that. Didn't enjoy that. This might be slightly older code. So yeah, we've created a neural network with these given layered. So now I'm going to go ahead and use nettrain to actually go ahead and train this neural network on some data. In nettrain, what it's kind of trying to do is minimize the loss function. So it's trying to get map our network so that it's able to correctly predict things to map to the data correctly. So, it's kind of the loss is like how far our network is predicting from the data itself. So let's go ahead and look at that. So what it's done here is we're looking at our trained neural network, and it's kind of applied it to it's looking at this is what it's predicting it to be. So if we look at what so let's have a look at what it's actually supposed to be without a uh, in this range. So this is the function. This is reality. This is what we're trying to look, and then this is what it looks like when we throw in some randomness, as it often is in reality. This is what we're trying to get to. We want our neural network to ideally be able to predict it for the true function, which is this. But in this case, we've kind of trained our neural network in such a way that it's kind of learned the data, but not the actual function it's trying to. So yeah, in this case, we've done some overfitting, which has was going to lead to poor performance of our neural network. So there are a few ways we can kind of combat this to avoid overfitting. So let's look at a few of those. So one way we can do that is doing some regularization. So this is kind of taking into account, it's fitting the data, but it's using some regularization. So here we're just, using nettrain. We're passing in this regularization option, which is quantifiable to a certain degree. And let's see how it performs. So here it's kind of like, it looks little bit closer to our true function we saw earlier. It's avoided overfitting in that sense. It's looking a lot better than this one. This is what it's supposed to look like, and so it's done well in that sense. Now it's doing this by it's getting the neural network to fit to the data, but it's also reducing the complexity of the parameters. So every time your parameter is changing to kind of map to the data, it's not enjoying that. It's reducing the possibility of that, so that you can't it's reducing the complexity of our parameters, so that that's more close to reality. So yeah, it kind of it's making it favor a less complicated model. So when it is complicated, it's just trying to avoid that. So let's look at another thing. So we can use dilution, where we're kind of like thinning out. So somewhat counterintuitively, what we're doing here was we're removing some of the data sets, and some of the data points or parameters even, sorry. And then considering that, it's then kind of retraining the model. So when you have so it kind of like induces unreliability for certain parameters of the model, so it doesn't become too focused on some parameters, um, and instead considers wider things, rather than it might focus on one thing in particular, but now it's considering the wider picture in general. So it's just allowing for a bit more generalization um, in general. So another way we can do this is with validation. So let's go ahead, and here we're actually generating some more data, some validation data, so that when we train our neural network, we're giving it some validation data on our data that we had. And then it's actually, during training, it's checking the performance of the model in comparison to some other data. Now this validation data isn't going to be changing any of the parameters itself. It's just giving the network a kind of a heuristic to its performance in the training process. And oh, I didn't show how it was fitting here. So here's dilution. Again, we're showing a little bit less overfitting, and again, a little less overfitting. It's not mapping to the data as such. It's more getting the general trend. So these three kind of methods to reduce overfitting are pretty standard, and you don't necessarily have to do them like exclusively. You can do them in combinations to kind of get to the best performance, which is what you're focusing on. That's kind of what you're looking to do in general. So, okay, so in summary, so what have we got here? So we've kind of in the Wolfram language, you have a bunch of functions devoted to unsupervised learning. So we didn't actually look at feature extract, but there are a bunch of unsupervised learning functions, but feel free to look at them in your own time. But also we have a lot of supervised learning. So we've got your classify and predict. So we have these in Wolfram language. We also have a lot of functions which use machine learning behind the scenes. So things like image identify and text cases. And also we have, because of how Wolfram language is implemented, we have a lot of automation and fine tuning behind this itself. And also there are a bunch of specialized ways where you can construct neural networks. I know we're going to be going into that in a few weeks, so do feel free to join to learn a bit more about neural networks. So there's also a bunch of further resources so that you can go ahead and learn yourself. These are all fantastic ways of learning a bit more about machine learning.